My name is Jackson Jandrew, and I'm presenting a study comparing different approaches to eliminating biases in second-order parameters derived from LiDAR data to improve the study of atmospheric gravity waves. This work was done by myself and Dr. Shinjiao Chu at the University of Colorado Boulder's Smead Aerospace Department in the Ceres Institute at the University of Colorado Boulder. One of our focuses in studying these atmospheric gravity waves is to quantify their strength. However, when you calculate these parameters directly from gravity wave measurements seen in LiDAR, these measurements are inherently biased, which can often make it nearly impossible to interpret the results. To understand why we need these methods and how they work, we must first understand how this bias is formed. A very useful statistic in studying these gravity waves is atmospheric variance. Variance consists of the average square of an atmospheric perturbation as seen in a parameter such as density or temperature. This perturbation is calculated by subtracting the background from the parameter itself. It is important to understand that an observed perturbation consists of two components, one representing perturbation due to atmospheric disturbances like waves, and the other portion simply representing noise in the measurement. It is clear in the expansion of this term in the equation below that the variance consists of three terms, part due to the wave and part due to the noise, and a cross term which is driven to zero upon averaging a sufficient number of terms. It is this bias that causes our issues. When you look at the figure on the right, you can see how strongly this bias can affect the results. While the real atmospheric result will look like the green line, you may only observe the black line, both of which exhibit entirely different trends in wave behavior. The purpose of this study was to test out three different correction methods, the variance subtraction method, the spectral proportion method, and the interleaved method. This study compared each of these methods by applying them to LiDAR data, which was taken at McMurdo, Antarctica, as well as to a forward model, which is shown in the right two plots. It's clear that each of these methods yields very different results, and this study explores when each one should be applied, as well as the pros and cons of applying each method.